How to calculate HIPPS valve closure time. Let's understand this with this example. In this sketch, we can see a pressure vessel which receives incoming fluid. Gas and liquid is separated. During a process upset, let's say there is a blockage in the outlet. Either the gas outlet is blocked or both gas and liquid outlets are blocked. The incoming fluid continues to flow into the vessel. This results in pressure buildup in the vessel. The pressure slowly builds up from normal operating pressure and keeps building up until it reaches its design pressure. And depending on the maximum pressure which can be generated from the upstream high pressure system, the low pressure system would be subjected to potential overpressure. This could lead to leaks or rupture of the equipment. The hazardous or flammable process fluid could release in an uncontrolled manner. This can result in harm to the people, assets, and environment. In such case, it is a common practice to provide two levels of protection. Once the pressure starts building up in this low pressure system, the high pressure transmitter will detect this pressure buildup and initiate shutdown of the inlet shutdown valves to cut off the supply from the incoming source. This is the primary barrier. In case this cutoff of inlet shutdown valve did not function, then the relief valve can act as a secondary barrier to prevent the overpressure. In some cases, there could be a HIPPS valve acting as a second barrier. A typical HIPPS valve is depicted here, where there are pressure initiators, a HIPPS logic solver which closes the final elements. So let's say this is a HIPPS valve, then the downstream is protected by the HIPPS valve, and there may or may not be a relief valve on the downstream. In such case, the primary barrier will be somewhere upstream to cut off the source, and this HIPPS valve will act as a secondary barrier. The two levels of protection is recommended based on codes such as API RP14C or ISO 10418. Irrespective of whether the IPF or HIPPS valve act as the primary or secondary barrier, it is important that these inlet shutdown valves close fast enough to avoid additional moles of gas building up the pressure into the downstream system and reaching its design pressure. If you have come across any of such queries, such as what is a process safety time, how to estimate a process safety time, and how to specify the closing time of the HIPPS or IPF valve, then this video will deal in answering all these queries. Let's try to understand how the pressure will behave in such an process upset event. In this graph, this is a pressure versus time graph. Prior to the event, the pressure in the vessel is at its normal operating conditions. As the blockage occurs on the outlet, additional moles of gas keeps coming in from the source and the pressure starts rising. When it reaches its high pressure trip set point, the initiators, pressure transmitters, will detect the high pressure set point and give the signal to the IPS logic solver, which then gives the signal to the final element, which is the shutdown valve, to close. The shutdown valve takes some time to close, and the incoming fluid keeps on coming into the vessel as the shutdown valve is closing from 100% opening to 0% opening. The pressure continues to build, and at this point the pressure has reached the design pressure of the vessel, or the relief valve set pressure if it is set at the design pressure in the vessel. The time taken for the pressure to build from the high pressure trip set point to reach to the design pressure of the vessel is called the available process safety time. The inlet shutdown valve should close fast enough such that its closing time is less than the available process safety time, so that the pressure buildup did not reach the design pressure of the vessel, and making the barrier effective. In order to calculate the process safety time manually, we'll make some assumptions. 1. The incoming fluid rate remains constant throughout the pressure buildup event. This is a conservative basis, since as the pressure starts building up, the upstream source flow rate will potentially reduce. However, for the purpose of this manual calculation, we will assume a constant rate throughout the event. Next, we do not take credit of any reduction in flow rate due to closing of the incoming valves. Initially, as these valves will start closing from 100% to 70%, then we do not observe any significant reduction in flow rate. However, during the final closure of 30%, there will be a significant reduction in the flow rate down to 0. However, we do not take any reduction in flow rate and consider constant flow rate throughout the event. For the purpose of this calculation, the pressure will continue to build even after the design pressure or the relief valve set point is reached, considering there is no flow going out of the system, because the intent of this exercise is to estimate the available process safety time between the high pressure trip set point and the design pressure. We are considering average fluid temperature and compressibility factor as same as that at the initial conditions. This is to simplify our calculation. Step 1. We will take note of the incoming liquid volumetric flow rate. So let's say the incoming fluid is a two-phase stream which comprises of gas as well as liquid. So we'll note down the incoming liquid rate in meter cube per second. In case the incoming flow rate is gas only, then we'll consider the incoming liquid rate as 0. Step 2. We calculate the molar rate of gas coming into the vessel using this formula. So we convert the volumetric rate into molar rate. In step 3, we calculate the total number of moles of gas in the system, in the underrated system at the initial conditions, that is the normal operating pressure temperature, where the subscript 0 indicates the condition at time t of 0. So the number of moles is calculated using this formula of pressure into volume of gas divided by compressibility factor, universal gas constant, and temperature. In step 4, we calculate the number of moles added into the system at time step t equal to 1 second. So the number of moles at time step t equal to 1 second is the number of initial moles of gas in the system plus the additional moles of gas added due to incoming molar rate of gas into the system. In step 5, we estimate the gas volume in the system at time step t equal to 1. So the volume of gas in the system is the total system volume minus the initial liquid volume into the system minus any additional incoming liquid which was added at time step t equal to 1 second, which was based on this incoming rate. In case the incoming fluid is gas only, then this becomes 0. In step 6, we will estimate the system pressure at time step t equal to 1 second. So we want to know what is the pressure buildup after time step t equal to 1 second using the universal gas law formula PV is equal to nRT. We also use the Z or compressibility factor to account for real gas behavior. So here the number of moles at time step 1 second is calculated in the previous step. The volume of gas at time step 1 was also calculated in the previous steps. The intent is, as the liquid from the two-phase comes in, the available volume or space for the gas reduces. So in case you have a two-phase fluid coming into the system, as the more amount of liquid starts adding to the initial amount of liquid in the underrated system, the space available for the gas reduces. Then we repeat these steps for subsequent time step of 2 seconds and so on until a time step of t seconds, where the system pressure has built up, crossing the high pressure trip set point and the design pressure of the vessel. At time step 2, we calculate the volume of liquid in the vessel, which is the volume of liquid at time step 1 plus additional volume of liquid which was coming into the system. Then we estimate the available vapor space or the volume of gas by deducting this volume of liquid from the total volume. Then we estimate the moles of gas at time step 2, which is the moles of gas at time step 1 plus the additional molar rate from the incoming gas liquid fluid. Then we calculate the system pressure at time step 2 using the moles of gas in the system and the available gas volume of the system, and so on. And finally, we estimate the available process safety time. The available process safety time is the time at which the system pressure reached the design pressure minus the time at which the system pressure had reached the trip set point. So the difference between the two is the available process safety time. The closing time of the valve should be faster than this available process safety time, and sometimes a margin of 1.2 is considered over and above the available process safety time using this formula. In addition, there is also a deduction of time to initiator, that is the transmitters and the logic solver, to process the signals. Generally, this is in milliseconds. However, sometimes a time of 0.2 to 0.5 seconds is accounted for each of them. And finally, you get the closing time of the shutdown valve. So your shutdown valve should close faster than this estimated closing time of the valve, which is our ultimate goal, so that this barrier is effective. If you would like to have an already built up Excel spreadsheet to perform the above calculations, then you can follow the link given in the description below to go to the blog page and then download the Excel sheet using this download form. We hope you liked this video. Do leave your comments on how you found this spreadsheet or these calculations. Where did you use it? Did it work well to complete your task? We would love to hear your feedback. Thank you.